Okay. And get that going. Do you believe me? 10 to the minus 10. No, so I think if two numbers agree on, if I tell you that they don't agree on any of the numbers, wait, is it 10 to the, it differs by at most, no. If I tell you that they're both 0 point, if they both start 0 point something, then they differ by less than 1. If they both start 0.3, then they differ by less than a tenth. If they both start 0.37, then they differ by less than a hundredth. Right? Because if they start 0.37, what's the smallest? One can be 0.37000, and one can be 0.3799999, but that's still less than a hundredth. If they differ on 3, they differ on less than a thousandth. If they differ on 4, less than a 10,000th. If they differ on 5, they differ on less than a 100,000th, which is 10 to the minus 5, I think. Okay, so we've got quite a lot to get through. So it's not that, I mean, I wish I could spend more time on this because it's not that hard, but think about it, it's in the notes. Okay, so Shannon noted that, okay, so this works also in binary. If I tell you that two binary numbers, if x is 10110 and y is 10110, and x is smaller than y, then how much can these differ by? Well, now instead of being 10 to the 1, 2, 3, 4, 5, 10 to the minus 5, they can't differ by more than 2 to the minus 5, right? So if I tell you that two binary numbers are both start 0 point something, they differ by less than 1. If they both start 0.1 and 0.1, then they differ by less than a half. If they both start 0.10, they differ by less than a quarter, right? So if they agree on b bits, they differ if two binary fractions agree on their first b bits after the binary point, then they differ by less than 1 over 2 to the b, which is 2 to the minus b. Okay? I know it's going a bit fast. I mean, packing information theory, packing the isolates coding theory, and I still want to cover half-plane coding. Ha! So this is a bit of a dense class, but so this isn't too bad. It shouldn't be too bad if you think about it in terms of decimal numbers, and then I'll take that as a compliment. I'm on track to not having anyone say that my course is easier than Norbert's. Okay, so if you take this and then you flip it around, you say, okay, if two numbers differ by a lot, then they can't agree. If two numbers between 0 and 1 differ by quite a lot, then they can't agree on very many binary on very many of the bits to the right of the decimal point. Right? So actually, if they differ by d, then I think they can, if you flip this around, I get the floors and ceilings mixed up, but they can only agree, if they differ by an amount d, they can only agree on their log d first I think it's floor log D. Floor log D. I'll have to think of it. Okay. We'll see this. It's right in the course notes, I hope. So you can see that if it says they agree on if they agree on B bits, then the difference is less than 1 over 2 to the B. So if the difference is bigger than 1 over 2 to the B, then they have to differ on one of their first B bits. Okay? So if the difference is bigger than this, then they have to disagree on one of their first B bits. Okay, it's just the converse. So, and I think that is so if you differ by D, you have to differ on one of your first floor log D, floor log D bits. Okay. So, why is that useful for building a code? Well, look, these are numbers between 0 and 1. Okay? So how much does S2, because the PIs were sorted, S2 differs from S1. So S2 minus, I'll make this bigger. S2 minus S1 is P1 by the definition of the S's, which is greater than or equal to P2. Okay? And what's the difference here? S3 minus S2 equals P2. So S2 differs from both its neighbors by at least P2 because the probabilities were sorted. So therefore, if we get rid of this and we do, right, we just check that this is recording. Yes. We work this out, so we say, okay, so we view this as a binary number. So S1 is 0.0000 so on, because it's 0. So S2 equals 0. And this is why I chose the denominator 128. So 37 is what? It's 32 plus 5, which it's not 64, it is 32, it's not 16, it's not 8, it is 4, it's not 2, it is 1. Is that right? Is that 30? If somebody has one of these cute little calculator things that converts between binary and decimal, this should be 37 out of 128. I think. It's not. This is about a quarter. So this is a quarter plus 8 to the 16th, the 32nd, whatever. Okay, we don't have time. Like, we hope it's true. So S3 is equal to 58 over 128, which is not 64, it is 32. 58, 32 plus, it is 16. 32 plus 16 is 48. It is 8. It isn't 4, it is 2. Okay, so I'm not going to do this for all of them. S4 is equal to 73, which it's 64, not 32. 73 is not 16. It is 8. It's not 4, it's not 2, it is 1. Okay. So, are people following this at all? These are just the binary fraction. These are just these sums as binary fractions. Now, by what we just wrote and erased here, because I don't have 3 boards, these numbers. So what S2 differs from S1 and from S3 by at least P2. That means that, that it can't agree on too many of its first bits. Oh, I think it has, yeah, it has to be a ceiling. Yeah, it has to be a ceiling. So it has to agree, it has to, so S2 has to disagree. Sorry, I said floor, I meant ceiling. With S1 and S3 on one of its first ceiling log 1 over P2 bits. Okay, because these numbers differ by at least P2, it has to disagree on one of its first ceiling log 1 over P2 bits. Okay. I know that's a bit fast, but I want you to sort of understand a little bit of information here. Okay, so you get it in machine learning. Fantastic. Okay, so that means that, well, if we look here, that means that it differs from S1 on its second bit, and it agrees with S3 on its second bit, but that means that if we take this prefix, these 3 bits, 0, 1, 0, S2 is the only one of these that's going to start 0, 1, 0. So we can use 0, 1, 0 as the code word, as the second code word. And notice that 0, 1, 0, it has length 3, and indeed 1 over P2, so 128. So ceiling of log 128 over 37. This should be at most 3. Okay, so this is saying that, so what is, this is 3, so this should be between 2 and 3. Okay, so you get this guarantee, so if you take, this has to be, right, so if we look at these code words, this is the code word. If we look at these fractions, we can pull out the code words for these numbers. So the first code word is 0, 0. The second code word is 0, 1, 0. The third code word is 0, 1, 1. The fourth code word, I can't see what, so it's S5 would be 87, so this would be 64, 70, 80, yes. There's a, it's not a 32, it is a 16, and then it's not an 8, it's like this. So now we would say this one, it has to be 1, 0, 0, and this one has to be something else, okay? Oh, thank you. Why just the first 3 digits? Because if we figure, because it has to differ by, at least, because it differs by P2 from the preceding sum and the succeeding sum, then we know that its binary representation has to differ by ceiling of log 1 over P2, and that's log 120, a ceiling of log 127 over 37, 128 over 37. And so that's going to tell us that it can't agree with these on too many of its bits, and in particular, it has to disagree on one of the first this many bits. And we look and we say, okay, it disagrees with S1 on its second bit, and it disagrees with S3 on its third bit. So if I tell you what I'm thinking of one of these numbers and it starts with 0.010, you know which of these numbers I'm thinking about. 010 uniquely defines this. So if you take that prefix, that is not a prefix of any of these other binary fractions. So you can take it you can take the prefixes of these binary fractions as a prefix-free code. Great, okay. We don't actually need to know that. That's just how Shannon did it, okay? It's not that hard, it's described in the notes. I mean, when I say it's not that hard, Shannon was a genius, nobody else had seen this. Like I said in the notes, Shannon's master's thesis was actually, he proposed using Boolean logic to model circuits. So, like I said, if you thought assignment 2, that question about building adders, was hard now, think about doing it when you couldn't actually talk about logic gates. You couldn't say that you're doing ands, ors, nots, XORs, whatever. You had to be like, yeah, it does. Like, who could do circuit design without Boolean logic? That was Shannon's master's thesis when he was 21. Boolean logic did exist. I mean, Boole introduced Boolean logic in sort of laws of thought. Actually, this is cool. When you're doing machine learning, you've probably heard of Jeff Hinton, who was he was actually a prof at University of Toronto. Now he's at Google, but he's the guy who did backprop and he got the Turing Award. Hinton, I think, is the grandson or great-grandson of George Boole. So anyway, which is weird because he's now proposing that. So he sort of opposes the idea that thought is logic, and so he's a family rebel. But anyway, yes, Boolean logic was around, but nobody thought that circuits were modeled by Boolean logic, or at least Shannon proposed. Like, oh look, I can model circuit design using and, or, not, XOR, Boolean logic, which did exist. And he proposed this, and so it's been called the most important master's thesis of the century. So that was his master's. That's not even what he's famous for. He's famous for information theory. But before he did information theory, he did a master's thesis, which was revolutionary. Okay, so Shannon was really good. So relatively speaking, this is not that hard. Okay, but what I want to, so I'm setting this up. I'm using like most of the class to set this up. You might not be 21 yet. You still have some time. Okay, so now we're going to talk about. Okay, I'm more. Okay, I'm not a Shannon either. I wish I were 30. Yeah, wish I were under 40. It's not bad. Okay, the alternative is worse. Okay, so getting back to it. So Shannon came up with this construction of prefix-free codes, which I'm not going to follow through with the example. But, so Shannon was a genius, but this is not an optimal construction. It shows that, yes, if you take these things and you say the sum of these some people in the class are probably under 21. They could turn out to be Shannons. Maybe. Okay, so if you take some, and you assume that you're going to use this many bits for the ith code word, a ceiling, you use that many bits for the ith code word, you're going to get pi ceiling log 1 over pi. This is strictly less than sum over the i's of pi log 1 over pi plus 1. this is equal to, since these pi's times plus 1, this is plus pi, and then sum over the i's, the pi's add up to 1, so this is just sum of I pi log 1 over pi plus 1, and this is h of p plus 1. So this is a strictly less, so Shannon code uses less than the entropy plus 1. We are not going to get to the proof of the lower bound, but it is in the lecture notes. Okay, so Shannon's construction, Shannon codes are good enough to prove that you're within 1 bit of optimality, within 1 bit of the entropy, and the entropy is a lower bound. But it's open, like, okay, but what if we actually want the best possible code? Right. And is that 4 minutes remaining? Okay. So this was sort of an open. Shannon didn't see how to do that, and there's another construction which is similar to Shannon's, except instead of doing these fractions, you sort of split. Called it was by Robert Fainall at MIT. And so that was about the same time. So this was in the late 40s. And then within 2 years, everyone realized that Shannon's information theory was fantastic. And so within 2 years, it was being taught at MIT as a graduate course. Sort of like, here's this new field. What can we do with it? And it was being taught by Fainall. And one of the people in it was David Huffman. And so Shannon said, I would normally make a joke about, like, I should do this, but I don't have time in this class. So Fainall said, like, you can either write the exam or you can do a project, and for example, you can figure out an efficient algorithm for finding the best code. Because in the course notes, there's an example of a Shannon code which is not as good as it could be. Where it's good enough, it's within 1 of entropy, but there exists a prefix-free code which is better. So so Huffman decided, okay, I'm gonna solve this. I'm gonna find the optimal code. And so he did. So the story goes that he couldn't figure it out, and he couldn't figure it out, and he was about to give up and start studying for the exam, and he finally figured it out. And it got published. It's Huffman's algorithm. He's famous for it. So we're going to cover that algorithm, but really quickly. So that's a greedy algorithm. So this is our introduction to greedy algorithms, allowing me to stuff a little bit of information theory into the course. Please read the lecture notes, because it has lots of cool stuff in this chapter, and it took me ages to write that. But first, because we have this problem that Shannon didn't solve and Huffman only barely solved in time to avoid the exam, we're going to do a little bit of a warm-up, okay, just in the time remaining. And the warm-up is going to be, suppose. Now, in the last class, we were talking about merge sort, okay? And imagine that I want to do an illustration of merge sort. So we're going to design a greedy algorithm for dealing with a problem related to merge sort, just as a warm-up. Okay, imagine that I take an array, and I want to illustrate how merge sort works, so I split it. It's unsorted. I split it into 2 unsorted subarrays, and I choose 2 people. I actually did this last year. I choose 2 people in the participants list, and I send them these 2 subarrays, and I tell them, okay, now recursively you split them up and send them to other people, and okay. But something goes wrong because, you know, it's online teaching, and it's just not reliable, and it's like people didn't hear, or people couldn't read the board, or something like that. So what actually ends up happening is people recursively sort their subarrays, but then some people send them back to me directly.
instead of sending them to the people they got them from. So I get a bunch of sorted subarrays, which all together form the whole array, but they're not merged together. So